at the other option where we measure distance using digital devices. It also doesn't take away the fact that corrections are made. Some could be embedded into the program that you use so that when you measure the distance, you have the corrected distance, but still some corrections take place. I will ask the co-host, do we still have a host, to mute whoever has their mic on? Let me assign Godfrey as the co-host. It has disappeared now. Okay, let me assign Nalugo Diana co-host so she can admit whoever is in the waiting room. If you lose your co-host rights, kindly let me know. So what do we expect to study in this class? Explain how total stations measure distance using the phase shift and pulsed laser methods. So we had a tape, we now have a total station, which is a device that we use to measure both angles and distances digitally in surveying. Okay. We should be familiar with different types of reflectors that can be used to measure distance. When we go along, we will see what a reflector looks like. And we should be able to understand that total stations can measure without a reflector. The normal procedure is that you have a total station on one end, you have a reflector on the other end, you send a signal to the reflector and it is sent back, and the distance is computed. But we can still do measurements without reflector. So we'll see how that happens. Be aware of safety issues while using total stations because of the laser component. So what happens with the total station is you have a signal that is generated into the distance measuring machine in the total station, sent to a reflector and sent back. And these lasers have classes, just like X-rays, gamma rays. So we should be able to know which class is safe for human use. If I am exposed to the laser light, what happens? Do I need to have some procedure made, or is the laser range for total state for human use even when I've been exposed? So I will first go back to this first slide where we have distance measurement, EDM. EDM is electromagnetic distance measurement. To the left-hand side, we have an EDM machine set up on a tripod. Then on the right-hand side, we have a reflector. And you see two arrows, one from EDM to the reflector, one from the reflector back to the EDM. That is how the laser light moves. So it is initiated or produced into the equipment. It runs to the reflector. Reflector is simply a reflecting surface, which we will look at different types. And then this light is sent back to where it was generated. Now on board, on the EDM or the total station, we will have a device that generates, it transmits, we'll have a device that receives, and embedded, we have a timer. So the machine is able to know what time the signal was sent, what time the signal is received. And the assumption is that this laser light is moving at the speed of light, which is 3 × 10⁸ meters per second. So once we have the speed, once we have the time, distance will be speed times time. Because we are two-way, it means the distance we shall have here is indeed a to and back journey. So it means at the end of the day, we will say if the distance between machine and reflector is D, then we will say D is equal to the time taken for the forth and back trip times speed, and 2D will be equal to the time times the speed. So D will be time times speed divided by 2. But all that is embedded into the software that's on the total station. So the distance you receive on the screen display, it will not be a two-way, but it will be a one-way. So they have already resolved for D. And like I said, there are corrections that can already be made in the machine, but you can also decide to do corrections after the measurement, like scale and you require, for example, to take temperature, you can you can have the measurements and put them in the machine, but you can also take the raw measurements and do the manipulation as you please. So that is the basic operation principle of electronic distance measurement. You have machine, you have reflector, you transmit, you receive. Basic method, distance speed times time. The co-host, can you mute the mic of, I don't know whoever has their mic on, but there's a lot of background noise. Kindly mute mics for all the participants, apart from those who will have a submission to make. So that is the basic operational principle of EDM. And now we are going to tackle bit by bit to explain in detail some of the other components and operations. So a total station I hope I am unmuted. So is that okay? Have we understood the operation principle of EDM? Can I have feedback before I proceed?
Yes, we have.
Okay. So those are the objectives which we ran through. So we now discuss some bit of detail. What is a total station? What is an EDM? What is a reflector? And the first slide here talks about what a total station is. Before we read whatever is written there, just below in the images or the figures, on the left-hand side, we have a total station mounted on a tripod. In the middle, we have a reflector. And on the right-hand side, we have a portable EDM, distance measuring device. So what we have on the left, which is the total station, the EDM is just a component of it, but it also has an angle measuring system. Then what we have at the center, which is a reflector, only the circular part in the middle is placed with mirrors. So these ones help us to bounce back the signal when it is received from the machine. The other option would be is that we have a timing system on the total station and also a timing system where the reflector would be. Then that means we would be able to send a signal from the total station and read off the distance at the reflector. But because the reflector has no timing system, that's why we receive the signal, we send it back, and then the manipulation or the computation is done to be able to decode the distance. So here we say, although taping is used regularly on site to measure distance, total stations and other EDM equipment are also used extensively in surveying, in civil engineering, in construction, because they can measure both distances and angles. So that is what an EDM is. those are few of the devices that we can use. And like I said, these measurements are also not free of errors. However, we have an option of doing corrections on board already by fixing in the corrections or the values that we require to be used to compute the corrections. But we can also download measurements the way they are and apply corrections to them. And when we use total station, unlike a tape where we measure slope and we can manipulate to get the horizontal, here we can take both horizontal and slope. So it means it measures the angle, it measures the slope distance, and then within the software or the system, it can generate for you the horizontal distance. But like we said, again, you can take off your slope distance, you can take off your vertical angle and still be able to compute your horizontal distance. Of course, now you'll not have to do corrections that we did in taping for slope, for sag and things like that, but you'll still have to do a correction for the scale. So that is what a total station looks like. Appearance of a total station is similar to that of an electronic theodolite. In the earlier classes, I think we have talked about a theodolite. And a theodolite is simply a device that measures angles. It doesn't have a device that measures distance. So when we have a theodolite, we add a distance measuring device on it, a digital one, then it becomes a total station. So theodolite is like a basic total station. Using vertical angle, total station can compute the horizontal and vertical distance components. This we already talked about. And I am sure we are all of mathematics background, so we remember our plane trigonometry before. It's a triangle. If I have 3 of the parts, then I can solve the other parts. So it's simply a combination of angles and distances for us to be able to get where we want to be. So what we have there displayed on the screen, if you have a question, you can raise your hand and we shall attend to you at any point during the presentation. So what we have on the screen there is a Geomax ZIPP02 digital theodolite. Geomax ZIPP is simply a model. And this is a digital theodolite. With a digital theodolite, you're able to read angles off the screen. With an analog or the traditional theodolite, you look through the telescope, that round thing you see, and read the measurements through the telescope. For a digital, you simply point where you want to read, and the angles will be displayed on the screen. You can choose to save them on the machine. You can choose to record them in a notebook. To use a total station, this is the very first slide that we talked about. You have your gadget at one end, and then you have the reflector at the other end. I will first run to, okay, this illustration here. To the left, we have a total station now. So it means we have a combination of the theodolite and an EDM. To the left, that's a TS02 Leica brand. And then to the right, we have a robotic total station. And extreme right, we have a pole, which is like a ranging pole, with a gadget, which is like a phone. And at the top of that pole is a reflector. So we can have different types of reflectors. So what we will use to measure distance is the total station. Let's consider what we have on the left-hand side, and then on the extreme right-hand side, we have the reflector. So we'll go back to our slide here. So the reflector is a prism attached to a detail pole, which is what we have seen in the figure ahead. And then the telescope is aligned and pointed at the prism. If we go to this slide here, you'll see that middle circular thing is a telescope. We have an eyepiece on the back side where the viewer will place their eye. And then on this other side, we also have a telescope is a combination of lenses. If you remember in physics in Nelson and Parker, there's a combination of lenses and mirrors to form a telescope. And if you consider that there was an illustration of a telescope, I think normal view with a relaxed eye. I will try to find the proper reference in Nelson. It shows you the content of the composition of the lenses and the lenses and mirrors inbuilt into the telescope. But you have the eyepiece lens, you have the objective lens, and this will help you to look through and view your target. So we said we have the reflector, then we point at the reflector with our prism. The telescope is embedded onto the total station. Measuring sequence is initiated and the signal is sent to the reflector. The signal supposedly is returned back, but you can see here that of course you will definitely lose some energy. So not everything that you have sent will return back. And in a situation that you do not have any feedback from your reflector, you will then not be able to have any measurement. So your screen remains blank. And even the machine will warn no signal or weak signal if it's not sufficient. And that's why we encourage that you do not take very long distances between your machine and your reflector, because by the time your signal bounces back, it has lost some energy. So it could be weak, you may not be able to read, but also you may not get the desired accuracy as the distance increases. And even when you are targeting, because you're looking through the telescope, so your reflector needs to be close enough for you to view it in the telescope. So after the signal is received back, it is analyzed to calculate the slope distance together with the horizontal and vertical angles. So this is simply a programs or formulae that's embedded into the software that's installed on the machine. So if the software is programmed in a way that you send signals, receive it back, what you have read is slope, convert slope to horizontal. This is a vertical angle, sine, cos, and things like that. Then that is what will happen for it to be able to generate for you the other quantities that you desire. A total station can also be used without a reflector. The telescope is pointed at the point that needs to be measured. So I could give an example of, let's say you have a point you want to measure. Maybe there is a big channel, a trench, or it's even in a swamp. Maybe your machine is this side of the swamp or the channel. You have a point across the other side of the channel and you cannot deliver your reflector there. There is no access. You can point a stable point. You can point at a stable point that you desire to read. Target your reflector there, make sure it is stable. You will not have any signal reflected back if your target is unstable. So target, make sure it is stable, you press the read button. As long as you have notified the machine that I am now reading in reflectorless mode. So activate the function and you will be able to read. It is something that we discourage because if you are working in reflectorless mode, it means wherever you target a stable surface, you will have feedback. And it's also something you need to check your machine for, and be sure that when you are doing measurements, you are doing measurements with a reflector. Otherwise, then you shall have feedback from different sources. So whereas we can use the reflectorless mode, we should use it only when we must. Because even when you're taking measurements, you are required to enter the height of your reflector pole, or what would be like the ranging pole. So it means if you are reading in reflectorless mode, you are actually estimating the height of where your reflector would be. So in situations that limit accessibility, we can use it, but we should try to avoid it as much as possible. And also, how much signal you get back when you're using reflectorless mode will depend on the reflective properties of the surface. Since we are engineers, I am sure we know some electromagnetic science. We know the spectrum, we know the frequencies and things like that. So how good a surface will be in terms of reflecting the light will dictate how much feedback of the signal you will have. If the surface absorbs the signal, then you will not have feedback back, and that means you will not be able to record any measurement. That is in the reflectorless mode. And most of the modern total stations now have that option available. But like I said, it is not something that we should use unless we have to. Is that clear?
Yes.
Okay. So what we have in a picture here is a motorized total station, or what we refer to as a robotic total station. In the earlier total station that we looked at, you have the signal being generated at the machine, and you have a panel or a display screen together with some buttons like a control panel where you manage your machine. So if you want to send a signal, you know where to press, signal is sent and received back. Now with the robotic total station, you have the total station, which you are seeing there mounted on the tripod. Then the gentleman you're seeing on the left is holding a pole. Onto the pole is a prism or a reflector, and you can see a gadget which looks like a big phone that's also clipped onto the pole. With the total station, the operation is manned on that phone-like. We'll call it a data logger. A data logger. It's simply like a phone. You have the software to operate the machine installed onto the machine, onto the logger itself. So what happens is every operation you desire to make is done on the data logger. So it means I don't have to stand at the machine to be able to make any measurements. I set up my machine, I center the machine, I level the machine, and I move away with my pole, which has a reflector and the controller. So whatever I do on the, whatever I command on the controller is what the machine will do, the total station. The only thing we have to ensure is the telescope has a line of sight. Okay, the line of sight between the machine, between the total station and the reflector must be clear, because once the line of sight is obstructed, the telescope loses connection with the reflector, then we are not going to have any measurements. So what the total station does, it keeps lock onto the reflector, but the command center or the computer is installed onto the controller. So whatever I command on the controller is what the machine will do. But like I said, the line of sight must be clear. The other limitation with this robotic is that you have to have clear connection between the controller and the machine, because it's like supposed to be two components in one. We have separated them. So it means there should be communication. It could be radio communication. You can use Bluetooth. You are now IT generation. So you know the several options we have to be able to have connection between the controller and the total station. But among them is the radio, Bluetooth, and that means you're also limited in range, because then if you go away, you can lose connection. So if you're using Bluetooth, you should know what range you will still maintain connection. If you're using radio, it means you still know in what range your transmitter and receiver will be able to communicate. The advantage with the robotic total station is that it can be operated by one person. The traditional total station, you will have a surveyor operating the total station. You will have a chainman or an assistant holding the reflector. So if I want to read on a tree, I'll ask the assistant to take the reflector to a tree and read it. If I have a robotic, I will move to the tree with the reflector and the controller, and on my screen, I am going to say capture point. So the machine targets the reflector, it auto-rotates, it sends a signal, it is sent back, and my coordinates are displayed onto the screen. It's a very good machine. It's modern model of a total station. The other probably limitation it will have is because it's doing a lot of maneuvers, then it uses a lot of battery energy. So you probably need two also batteries. So when one runs out, you change and fix the other. So that is a robotic total station. What we normally use to facilitate training for learners initially is a theodolite and a total station. Theodolite, a tape, and total station. But at the department, we also have a robotic total station that we can use in the advanced classes for us to be able to display or even understand or illustrate how technology has also advanced over time. So all that we have talked about, what we have on that screen is a total station. Again, to the left, we have the traditional total station. To the right-hand side, we have a robotic total station. This one that we had here is a Trimble, and this that we have here is Leica, and these are just brands like we see Toyota and the other car brands. So Leica, Trimble, Geomax, those are simply the brand names. And also even the brands will have different models, just like you can have a car model 2000, 2001, 2002, and every other advanced model comes with additional privileges. So like the earlier Leica total stations, we were not able to transmit data using Bluetooth. The advanced one, you are able to transmit information using Bluetooth. Some you would have to connect a cable directly to a computer. The advanced one will have a USB port where you simply insert your flash, send your data there, and then transmit it to the computer. So every other model comes with an added privilege. Any questions so far? Nothing. Okay, so most stations have a distance measuring range up to a few kilometers when using a prism. Prism, when I say prism reflector, it means the same thing. A range of at least 100 meters in reflectorless mode. And here we can have an accuracy of 2 to 3 millimeters at short ranges. It increases as your range increases, because even as your range increases, even your capability of targeting using your telescope is also limited. So that's why we need to restrict our distance ranges to keep them as short as possible. If manufacturers can read up to 2 kilometers, you will have already some basic knowledge in surveying. Then it doesn't mean that you should push it to a maximum of 2 kilometers, because at 2 kilometers, you will even struggle to see the reflector. So it means even your targeting will be just okay, but not as good as it would have been at maybe 200 or 300 meters. And now this brings us to distance measurement or measuring methods that we use for EDM. And this is purely physics. So we could have 1 or 2 people explaining the phase shift method briefly, or the pulse laser method briefly. This is purely physics, I think, under waves, distance measurement using the pulse method or the phase shift. Yes, Godfrey. We have a hand from Godfrey.
Okay. I want to explain the pulse.
So you put on video.
Yes, please.
So need to get the distance between the 2 points, right?
Yes.
So we are going to get the time taken for the pulses to move from the instrument to the reflector, then back to the what? Back to the instrument. Okay, right?
Yes. Yes. So, Godfrey, which method is that? Is it the phase shift or the pulse laser?
No, this is the pulse echo method.
Godfrey, have you finished submitting, or you also want to talk about the phase shift? So anybody to talk about the phase shift method? Okay, nobody. I hope everybody remembers that we have marks for attendance. So every time we answer a question, there is a mark dropped somewhere. So Godfrey has talked about the pulse laser method, which is what we repeatedly use in the operation. When I explain the operation principle, is that we have a signal at the instrument, it is sent to the reflector, and then it comes back, and the distance is computed using distance is equal to speed times time. And what we have on the screen is the phase shift method. So we have machine A, we have the reflector B, the signal is sent from A to B, it is sent back from B to A. So if you look at figure C, we have AB, A prime. So ordinarily in total, the distance we have moved is not D, but 2D. And that is why we end up with 2D is equal to distance, rather is equal to speed times time. So for us to be able to get the one-way distance, then we divide by 2. Now, that is the pulse that Godfrey has talked about. Now, what happens in the phase shift? We'll use the same approach. Again, like I said, this is physics, and I am sure all of us are of physics background, unless you guide me otherwise. But the assumption is that we have all done physics, so we know the behavior of waves. We should be familiar with frequency, with wavelength, with amplitude. So again, here we have 2 points A and B. We assume that our signal is generated at A, it is sent to B, and then it is sent back to A. And our signal, which is the laser light that moves from the machine to the reflector and back, is represented as a wave. And this wave has frequency, it has the wavelength. So all we need to do is find how many complete cycles of our signal we have from A to B back to A, which is now A prime. And once we know the wavelength, then we should be able to convert these cycles into linear distance. So we know that C is equal to F lambda. C is equal to F lambda, where C is the speed, lambda is the wavelength, and F is the frequency. We also know that frequency is inversely correlated to T, which is the period which a wave takes, rather a cycle takes. One cycle, the time it takes to complete one cycle. Basic physics. So once we have identified how many complete cycles we have, then we convert that into distance. But not all the time do we have complete cycles. So that's why here you see we have n times lambda m, where n is the number of complete cycles. And then at the extreme right, we have change in lambda m. This is a fraction of the cycle. A fraction of the cycle that doesn't make a complete cycle. So then we take the number of complete cycles and then we add on that fraction of the cycle towards the A prime, and then we convert this number of cycles to distance. And that is the phase shift method. Have we understood the two basic principles that EDM uses to measure distance?
Yes.
So all this is explained in these slides that we have here. We know the speed of light, 3 times 10 to the power 8. If we approximate, we said C is equal to F lambda. That means wavelength is equal to speed over F. We have speed. So that shows up how you add up the two complete and the fraction part to be able to get the total distance. This, the last bullet talks about how we find n, the complete number of cycles. That is the ordinarily the program that's embedded into the software. Of course, the machine determines for you the n, even the fraction part, but just to read and understand how the n is resolved. And here it says the phase shift method is also applied or employed or used in GPS equipment. And here we are referred to chapter 7 to read more about GPS and the phase measurement method, though GPS also uses both the pulse and the phase, though the phase is more accurate than the pulse. So here we have the pulse methods, which we have already talked about, which also Godfrey talked about. So those are the different methods that can be used to measure distance electronically. So when you have a total station, the best you can do is find out which of those it uses. Even find out if it has both, and you have to have, you have the luxury of choosing which to use. Most of them will simply give you your measurements. So it is up to you to look back into the software embedded and find out which method is actually being used. When we use GPS, then we have the luxury of either using the code or the phase, depending on what software we are using to do the manipulation. So that is the basic methods that we use to measure distance using an electromagnetic distance measuring device. Any question? There is a hand from Davis. Davis, do we have a question?
Yes, madam.
Yes, Davis.
For example, which kind of softwares do you have to enter the data in so that you get the results for your data collection from the field? Which examples could you recommend?
Okay. Davis, we will have every manufacturer will produce their own software. So if, for example, you're using a Leica total station, it comes along with the Leica software. So to, and they most of the time make it incompatible so that when you have a Trimble, you may not be able to download data or even to use data from the other software. So we have restrictions, but most of the manufacturers will design their own software. But specifically for total station, software is not a big issue. What happens is when you do measurements in the field, you can choose to record raw measurements or unprocessed measurements, which is angle and distance. And then you compute the coordinates using a software of your choice, which can be Excel. We also have an option where you, from the machine, you directly download X, Y, and Z, and you do further manipulation with it. So mainly for total station, the major output is either angle and distance measurements or X, Y, and Z, which is really figures. And so you can either record manually in the field, you can record on the machine and transport that information from the machine to your computer and use Excel or any other software that you desire to use, depending on how you want your end product to look like. Some machines do not have Bluetooth, like I said, so you may need to connect a cable from the machine to the computer. And those are the specific machines that have compatibility issues. But if I have a Leica total station and I need to connect it to a machine that has Leica GeoOffice software, then I may be restricted if I don't have the software. When you are buying, you buy machine separate, software and license separate. So you'll find most of the people have the machines, but they have not bought the software. So then that also comes in the, when you are buying a machine, what do you look out for? Find a machine that has Bluetooth. It means you can share data easily between gadgets that have Bluetooth. You can have a USB port, insert your flash and remove your XYZ or angles and distances, and then you can manipulate them whichever way you please. So for total stations, the software of manipulation of data is really basic. Software, Excel, and then maybe after sorting your data in Excel, you may want to take it into a mapping software, AutoCAD, and any other software that you desire to use. So the only time you will find you need the software for a machine is mainly to share or to export the data from your total station onto your computer. Thereafter, depending on the end product, you can decide what you want to use. So it means if your machine can only share data using a cable and you have to have the software, then you have to look for the software. Have I answered your question? Okay, Davis is not responding.
Yes.
And from I have, okay. So we have a hand.
Thank you so much.
Cheng.
Excuse me.
Oh, Cheng, you can ask.
Yes, madam.
Yes, please.
Hello?
Yes, so Cheng, we can hear you.
I wanted to understand what kind of data does the total station give us? Because those equations you have given us for the calculations, are they calculations I, as the surveyor, am supposed to do? Or are those the background calculations that the machine does? And then, okay, I haven't understood exactly what kind of data it produces out for the two kinds of methods, the phase shift and the pulse method.
Okay. Now, the pulse and phase are different techniques for measuring distance. So we have an EDM machine embedded into our total station. We press a button, it returns a distance. It can be a slope distance, it can be a horizontal distance, it can be both slope and horizontal. So that is embedded into the software that is running on the machine, enable you compute the distance. So yours is to simply press a button, a signal is sent, it comes back. On your screen, you have distance and angles displayed. And like I said, you will have, it measures slope, but remember it also measures along angles. So you can also read off the horizontal distance that software has computed. So we are able to read off distance, both horizontal and vertical. We are also able to read off angles, both horizontal and vertical. So one option is we record angle and distance, and then we use our plane trigonometry approach to compute the coordinates, X, Y, and Z. But also this total station can directly give us X, Y, and Z, because embedded into the software is also algorithm for converting the distance and bearing into change in x, change in y, and they add those change in x, change in y onto the known coordinates of your station to be able to generate for you coordinates of the point where the reflector is. What we normally do is when you record distance and bearing, then you actually can be able to check if you think there is a problem. If I have 2 points, I have the known point where a machine is set up. I have an unknown point where the reflector is. I have computed coordinates. And I think instead of having a distance of 10 meters, the machine is giving me 12 meters. So then I can look at the angle, I can look at the distance and try to find out what the problem is. Also, sometimes you want to apply corrections that are not embedded into the software that the machine runs. So it means I am able to get off my angles, I am able to get off my distances, and I can apply whatever corrections I want to these measurements for me to find the coordinates. And as we will study later in some of the methods of finding or fixing position or finding coordinates, the main one is traversing. When we traverse, we record distance and angles and not coordinates, whereas you have the luxury of recording coordinates. We prefer to do distances and angles so we can do the checks. If we find any corrections, make the corrections and we compute the corrected coordinates ourselves and not in the machine. But to summarize everything, we are able to read distance and angles digitally. It means we display on the screen, we can record or save on the machine and transmit later. We can also read distances directly, but we can also compute corrected coordinates from the angle and distance measurements. So Ocheng, I don't know if I have answered your question or if we need clarification.
Thank you, I've understood.
Okay, there was another hand up, it went down. I don't know if the question was answered or if it's still pending.
The hand is still up.
Okay, so you can proceed and ask the question.
Yeah, good afternoon.
Good afternoon, Gabriel.
Yeah, I would like to just know the difference between digital pulse counting approach and the null point approach in terms of getting the phase difference between the two signals.
Between the two signals, you want to find the difference between the two methods?
No, I want to just get to know the difference between the counting approach and the null point approach when we are getting the phase difference between the signals received and the ones transferred, like when you're using the phase shift method.
When you are using the phase shift method, Gabriel, we are not going to get into the nitty-gritties of the wave approach of computing distance, but I will refer us to, I think I put some references here in Uren and Price, but also Nelcon. Actually, Nelcon is the simplest, very, very simple. It clearly gets us through the initiation, how we make the equations based on the wave principles, the amplitude, the wavelength, how we can convert the number of cycles, Here we talk about the ambiguity resolution, that is determining the number of counts or the number of complete phases. So I will refer you to Uren and Price. I will refer you to Nelcon. And there's a very, very simplified and detailed account of how we derive all the formulae until when we get to the final that is embedded into the software, and also the choice of which to use when. Unfortunately, when we buy a machine, we have not even queried to see which kind of approach is being used, but the nitty-gritties until when we generate the formula is all clearly stated into that.
Thank you, Madam.
Okay. So, if there is no any other question, then we shall proceed to, now this is basic trigonometry, shows how we run from horizontal slope, something that we also discussed in taping. This is about accuracy. So if you're buying a machine, they will tell you it can read, okay, ordinarily maybe to 2 millimeters to 3 millimeters, even angles to this second, so that you're able to know the accuracy that you can attain. And also sometimes when you are provided with the terms of reference from a client, they already state their expectation in terms of accuracy, so that can guide you on what machine to use. If they want 1 millimeter and you're using a total station that gives 2 millimeters, then it will definitely not pass. So this is just to attach an accuracy component, and also to indicate that different machines will not give the same accuracy. So this brings us to, we have talked about the machine, the EDM, we have talked about the reflector, and this indicates the different types of reflectors that are actually available. And I'm sure you will look at this when you do the practical part of the course. Unfortunately, they are black and white, but we will still be able to see. What we commonly use is what is at the center to the left, at the center to the left. And at the center to the left, we have the single. At the center to the right, we have a triple set of them. So those are the different types that we use, and embedded into that reflector is surfaces, mirrors that will play around with your signal and be able to send it back. I am sure we have done lenses, that's optics in physics. So we should be familiar with reflection of light, properties, and things like that. So all this reflector needs to help us do is receive the signal and be able to send it back. And how much signal is sent back is what will determine if we have a measurement back at the machine or not. And when we are targeting, we target the center of that reflector. So that circular part, just at its center is where we target. So that is how a reflector looks like. And this is a handheld laser machine for rough measurements, just to indicate that we don't have to have very sophisticated total stations to measure coarse measurements, since we can even use tapes depending on the required accuracy. We can also use this handheld device to measure distance. And maybe like we said before, if you desire to know which approach is being used, then that would be part of the manufacturer specifications or even the software specifications. Not all measurements that are done using a total station are free of errors, simply because we don't have to pull and do tension. Because we do not expect a sag, it doesn't mean that our measurements are still free of errors. And like I said, when we do traversing, we prefer to have angles and distances, and then we can correct them before we produce the final coordinates. So just like tape, we still do corrections here, only that with the total station, you may have the luxury of already incorporating the correction models into the operation while you are in the field work. For example, there's a correction we normally make for scale. And this correction is because when we are measuring, we are assuming that the Earth is a flat surface. But we very well know that it is not. The best probably estimate would be a spherical surface. So it means if I am measuring distance between a point here and a point in South, can the host mute participants who have unmuted their mics? Okay, so if I'm measuring distance between here and South Africa, and I am assuming that we are on a flat surface, it's definitely not a good assumption. So then when we are measuring distances, we need to take care already of the curvature of the surface of the Earth. And that is the scale correction that we make. Now we have an option of already putting in the scale correction in the total station as we read. Otherwise, if we desire not to enter the correction as we read, for scale, we shall put 1. So it means nothing is being made to adjust the observed distances. And then when we download the distances and the angles, we can apply this scale correction to the distances that we have measured. But like I said, you may also be able to already do it when you are doing measurements in the field. So we can have instrumental errors as well, just like we did for the tape. Remember we said we have, sometimes we have the standardization correction where they say a tape is 30 meters when it is 30.01. You can also have your 0. Instead of starting at 0, part of it has broken, or for some reason you're not doing the measurement at 0. Those are also systematic errors. And that's the reason we actually have to have our total stations calibrated at least once a year. And when you're on a project, they will always ask for calibration certificates for your equipment. If we say a tape is 30 meters, is it 30 meters after 1 year? Is it still the same after 6 months? So that's why we need to do calibration often, but minimum is 1 year. So that if we are using this machine and it tells us that we have measured 30 meters, should we trust that it is 30 meters, or we need that standardization in quotes correction? So with emphasis, when you're borrowing, when you're hiring a total station, a level, make sure you have looked at the calibration certificate. For leveling, we have the luxury of doing a 2-peg test to check if it is in check. But yeah, calibration is very, very important. Otherwise, then we shall have systematic errors to deal with. So we have already talked about some of the errors, but this is also some bit of reasons or causes of the out of calibration or standardization. So we are saying since calibration parameters can change because of mechanical shock, you're moving machines on a bumpy road, they are not well protected in their cases. There's temperature issues. The manufacturer said your machine should be kept at 20 degrees centigrade. It should be aerated. We keep our machines in the cases all the time for security. Rough handling, a machine may fall down and the user doesn't tell it has actually fallen down. So because of these very many reasons, we need to take care of all those uncertainties to make sure that if we are saying it is 300 meters, it is actually 300 meters. Or on the, if you think about it, like I am measuring 2 points, it's okay. What if you are measuring distance subsequently for 100 kilometers? It means even if you lose a millimeter for every 200 meters, by the time you get to 100 meters, you're going to be so many meters away. And that is what happens in real life. You have an engineering route project, it's a road, it's a railway, it can even run 300 meters. So everything counts. Don't look at the independent small stretches as small distances. Ultimately, your result at 100 kilometers can be affected by a small mistake just at the beginning of the project. We also discourage moving equipment on public transport because then you do not have any guarantee. You're seated in a bus, your machine is in the boot of the bus. There's matoke on it, there's timber and whatever it is. So we discourage moving equipment on public transport. Have it in your field car, at least ensure that it is being properly transported. And like we have said, after every 1 year, have your machine checked and a calibration certificate issued. If it's out of adjustment, the calibration centers know what to do. They also know what checks to make sure that it's doing the right thing. There was a hand up.
Yes, madam, I have a question.
Yes.
Actually, I have 2 questions. If most of these machines are, how are they calibrated and who does that? And then second, and actually say of 2 millimeters. And then the machine just gives you a certain distance. You read it off, so you don't know. The accuracy can be positive or negative. So if you read it off, how do you know how to correct that distance when you don't know if it is greater by 2 or less than 2?
Okay, I got the second question. I missed the first question.
The first one was on calibration. Who does the calibration of these machines?
Okay. I missed the name, but calibration. There are calibration centers that have the mandate to calibrate this equipment. In Uganda, there is one that is called Data Grid. It is somewhere in Entebbe. And there is also one in Nairobi at the regional center for mapping resources and development, RCRMD, which is what we normally use here. We send our equipment there, it is checked, and then certificates are issued, it is sent back. Now, in these calibration centers, there are those machines that we use as a standard. So for example, if we know a tape is supposed to be 30 meters, so it's measured against a standard which we are sure is 30 meters. So in this room, they will make sure the conditions suit what is desired. If we know a tape is supposed to be kept at 30 degrees, we'll make sure that the temperature is that. And then we'll have things like the collimator, and there are some machines, some smaller even machines that we have discussed before earlier in physics and other courses that they will use to check the angles. I have talked about a two-peg test, which you can do simple check. This one doesn't even need sophisticated equipment or expertise. So these calibration centers are equipped with equipment that is to standard that will help us to check. So if you measure an angle with your standard equipment, it's 60 meters, rather 60 degrees. If you measure with your equipment, is it 60? Then if it is not, there is a problem. Where is the problem? And then they will use this sophisticated equipment to be able to make the necessary adjustments to have it in its proper state. So one is data grid in Uganda, nearest is RCRMD. For GPS, they will have international stations. I know there's one in Dubai. You only have to make sure that before you send your machine to a calibration center, you are sure it is the right place. And they will have clearance from the national bodies, Bureau of Standards, so you can even cross-check with them and you see if they qualify or not. Otherwise, you can send your equipment there and it comes back in even a worse state. So that's the calibration. However, the other problem is when you are sending equipment out of the country, then when it's coming back, you will have to deal with URA. So before you ship them out, you need to have the proper paperwork, which indicates that machine came in, it was taxed, it's now only going back for service. So that's why anybody would prefer to use a local station that does the work. And then the other question was about accuracy. Is if I buy a total station and the user tells me 2 millimeter, we can measure to 2 millimeters, and there's a correction to make, then how do I take care of this correction? Number one, the easiest would be, again, what I said, take your raw observations, do the adjustments that you desire to do. So I know if it's out of calibration, this is the standardization. If temperature was supposed to be 20 and it is 30, this is the model I use, and I can make those very many corrections. I talked about the scale where we assume that it is a curved surface, where we assume that it is a horizontal, yet it is a curved surface. Compute that, then do the corrections. Now, what happens is when they are making these machines, they have installed programs on the machine. And these programs will take care of all those issues that they desire to take care of. However, that's the difference between you, let's say an engineering surveyor or a surveyor, and simply somebody who can operate the machine. Is that you, that the surveyor or the engineer knows what is happening in the machine. You very well know what program is running, you know what corrections are being taken care of, you know what model is being applied. You could have different models. Which model is used to cater for this correction? And the only way you will find out, again, is like I said, a manufacturer will give specifications. Unfortunately, most of the commercial software is a black box. You buy the software, you buy the license. Well, you do not know if it's using pulse method, you do not know if it's using the phase method, but all this is incorporated into the software. So once you buy the software, you have the manual, you can actually run through and see which algorithm or which formula is taking care of which correction. If you are not comfortable, like we normally do, take the raw measurements, compute the corrections yourself, and know that I have catered for standardization, I have catered for the scale and whatever other correction that you have to make. Then you will know that I have taken care of all that I need to do for me to be able to minimize the errors or to maximize my accuracy. Have I answered the questions?
Yes, madam. Thank you so much.
Okay. Any other question? There's none. Okay. And now this explains some of the errors. And what we have here is the horizontal collimation error. How do I think? Okay. I can place it. So when you read here, they will talk about horizontal collimation error and how it can be fixed. And what I have in the slides is somehow summarized, excludes the detail, but what I will post on Muwele after the class, it includes the algorithm. Includes okay, I lost connection. I don't know at what point I lost connection.
What you will ask?
Can I know at what point I lost connection?
At the beginning of horizontal collimation.
Okay, at the beginning of horizontal collimation. So I was simply saying we have a detailed account of some of the corrections that we will have to deal with, just like we did for taping. And I said the detail of this is in our textbook, Urine and Price, but also the slides that I will post clearly detail the several
your screen.
errors. Oh, I'm not showing the screen. Oh my God. Okay, so can we view the screen now?
Yes, we can.
Yes.
Okay. So what we have there is the horizontal collimation, and there are many others. There's a tilting axis, there is a compensator index error, the vertical collimation error, and all these are instrumental errors. And all these are only checked and addressed through calibration. As a layperson, you will not be able to correct for any of these. So you can only do this by calibration. So if we take an example of this horizontal collimation, you can see that we have the line of sight through the telescope, and then we have the tilting axis, which ordinarily should be perpendicular, so that the angle between the line of sight and the tilting axis should be 90 degrees. It may not be 90 and you will still use your machine. And unless you take this machine to a calibration center, you will actually not know. So once you have your machine, when you take it there, they will have gadgets to check for such anomalies. They check the line of sight, check the tilting axis. Is it 90 degrees? That passes. Is it not? Then they adjust whatever they have to do to make sure that it is that. Then now we have the tilting axis error, we have the compensator index error, we have the vertical collimation. And all those are instrumental errors addressed through calibration. Yes, or Cheng?
Madam.
Yes, please.
What are phase measurements? Because I'm seeing in the write-up, you're saying that horizontal errors can be eliminated by, is it two phase measurements? What does phase measurement mean?
Okay, Ocheng, two-phase measurements. I am going to talk about two-phase measurements for purposes of answering your question, but later on, when we get to angle measurement, it shall be quite clear. So for those who don't have an idea yet, they shouldn't be worried. Ocheng, when we are reading using a total station, we have what we call face left and face right. A total station will have a vertical circle. It will also have a horizontal circle. So if I am taking horizontal measurements, if my horizontal circle physically is on the left, that is a face left reading. If my horizontal circle is on the right, that is a face right reading. So ordinarily we take measurements on face left, and then you transit. Transiting is you rotate the telescope. So I am standing here, the telescope is in front of me, my circle is on the left. I take my first reading, then I tilt the telescope 360 to face my direction, rotate clockwise. Now my horizontal circle is on the right-hand side, and I take another reading. Now the check is the difference between face left and face right should be 180 degrees. So if I sit at point A, I target point B, I feed in a horizontal angle of 0, 0. I transit the telescope, I take a reading on face right. Ordinarily, or if my machine were perfect, I should read 180 degrees, but it never is. However, there is a range within which you should not get worried. There's also a range beyond which we should get worried. So if it is way beyond 180, then you need to worry. If it is within, you don't need to worry. And what commonly happens is, because at the back of my mind, I know that when I transit, I should read 180, then I will force my reading to be 180. When you force your angle to be 180 because you have transited and you think it should be 180, at the end of the day, when you compute your coordinates, they will be off. So if I feed in 0, I transit and I am reading 180 or 179 degrees, 56 minutes, 53 seconds, that is what you write. And that is part of the corrections that we shall make, because we know at the back of our minds that it's not going to be 100%. correct. So then we shall make a correction to cater for that. Have I answered your question, Ocheng? Ocheng, have you disappeared? Yes, I have. Okay. So we shall discuss the first left, first right business in more detail when we do angles, but that's ordinarily it is that we take the second face just as a check. And now what we have on the screen is also another way of checking. You have points 1, 2, 3. You measure distance between 1 and 2, measure distance 2 and 3, and then measure distance 1 and 3, and compare the deviation. Ordinarily, if you add 1 to 2, it should give you 1 to 3. So compare them and check. Like I said before, in surveying, we do not have error-free measurements. So we don't expect that when you add L1 to L2, 3, then you get L1, 3. It never happens. But if it's within range, then we apply the corrections to try to make it as accurate as possible. The first one, instrumental, then we have atmospheric also effects. And here they are talking about temperature, pressure, relative humidity. The speed at which the transmitted laser travels through the air at standard temperature. Changes in these atmospheric conditions change the density of the air, which changes the speed at which the laser travels, resulting into an error. Total stations can be adjusted for atmospheric corrections by inputting changes in temperature. So it means that when they design the software that the machine is using, assumption is the speed of light is 3 times 10 to the power 8. Any change in the environment, remember this is the speed of light in vacuum. But now you are traveling, your signal is moving through a different environment, which may affect the speed. So we can have an advanced signal or a delayed signal. Both of them will have an effect on the final distance. So ordinarily what would be ideal is in your software, when you're operating the machine, you have an option to enter the in situ temperature or the physical temperature. So carry your thermometer, measure temperature and put it in. You could also have software that have models, temperature models. So it interpolates and says at this point, this should be the temperature. But like I said, the best option would be to take your own temperature, compute your own correction, and adjust your measurements according to what you have computed. But this will be negligible, especially because for total station, we measure relatively short distances. It's not like GPS where a signal is moving from a satellite 20,000 kilometers from the surface down onto the surface. So some of these we can actually ignore. But if you choose not to ignore, then you should already know what to be worried about and how to handle and what should pass without worrying you. So like I said, if you check urine and price, there's a whole topic on total stations and electromagnetic distance measurement. There's a lot more than we have presented here, the algorithm and the corrections that we have to make, why we have to make them, and what accuracies do we attain, when should we use a tape and when should we use a total station, how much should we be worried if we use a tape, when do we use reflectorless mode, why should we use it and why shouldn't we, And if we did use it, then what is our expectation in terms of the accuracy? So that's the end of our today's presentation, and it also closes the distance measurement exercise or topic. And I wanted to stop sharing the screen so I can look at Mwele. So we see what we will have to do next. Let me screen share again this Mwele. So we did introduction, we have finished distance measurement. I have posted the notes for taping. I am going to post today notes for EDM, total station and EDM. There's also a method of distance measurement that we refer to as optical distance measurement, or DM. And we did not include it here because it's rather now outdated. So we chose to talk about the methods that are still being used, but that doesn't stop us from reading about it. So as part of your exercise, you can read about optical distance measurement. And that means